Thank you for the introduction. So, in this work, we present a practical and scalable database management system that achieves a unique combination of privacy, versatility, and security. The system achieves both query privacy and fully robust access control while supporting a rich search functionality, including arbitrary Boolean expressions. It extends the blind Seer system, which was first presented at Security and Privacy last year. Blind Seer stands for Bloom Filter Index Search of Encrypted Results, which alludes to its use of encrypted Bloom filters for supporting private search over encrypted data. The goals of Blind Seer are threefold. One, to protect the privacy of a client's query from the server. Two, to protect the data in the server so that the client cannot learn anything about the database other than the results of its query. And finally, to implement access control in the form of policies restricting what queries the client can ask, even though those queries are kept private. However, a drawback of Blind Seer in its original form was that the access control was not robust. It was only secure against a so-called semi-honest client. However, a malicious client could really ask any question it wanted of the database without risk of detection. So our result obtains fully robust access control without sacrificing on query privacy or overall performance. Private database querying is an age-old problem in cryptography. In its most general form, a client sends a query to a server who holds a database, and ideally the server should learn nothing about the query, and the client should learn nothing about the database other than the results of its query. There are a host of perfect theoretical solutions to this problem that can be built from such primitives as secure function evaluation, private information retrieval, and more recently fully homomorphic encryption. But the ongoing challenge is in designing truly practical solutions to this problem, especially for large-scale databases. In fact, there is a fundamental limitation on the efficiency of perfect solutions to this problem with a single server and single client. To completely hide the query from the server would be required to do a linear amount of work in the size of the database. If it doesn't examine every record in its database on a query, then it will at least discover what information is not being returned by the query. So practical approaches to this problem turn to relaxed models, such as a split server model, where the server is split into two non-colluding entities. One can be thought of as the data owner, and another a proxy server that facilitates the search protocol. And the privacy of the query should be held with respect to both the index server and the server, as long as they are not colluding. And in this setting, sublinear solutions are possible. Now, this is the model that Blind Seer follows. In Blind Seer, the server is the data owner. It builds an encrypted index to its database that it sends to what we call the index server. Sorry, it's cut off from the slide, index server. And the index server interacts with the client to process the client's private query on its encrypted index. The client receives back encrypted records that satisfy its query, and finally receives decryption keys to decrypt these records from the server, but in a way that hides from the server the identities of the records that are actually being returned. There is a fourth entity that we call the query checker, whose responsibility is to enforce a policy restricting what questions the client can ask without knowing what the client's questions are. Now, the query checker can be logically associated with either the server or the index server. We only depict it as a separate entity for sake of generality. So Blind Seer achieved provable query privacy and data security up to bounded information that is leaked in the form of randomized data access and query patterns. Now, this trade-off allowed it to achieve a combination of security, privacy, and efficiency and versatility that was not before achieved. So it supports a very rich query set, including arbitrary Boolean formulas over both keyword searches, range searches, and more. And its performance was comparable to MySQL, performing within a factor 3 on many queries, and it was tested on database sizes ranging to 10 terabytes with 100 million records. Previous work on private database systems was either theoretical in nature or practical but achieved privacy only for limited functionalities such as single keyword searches or conjunction queries. Now, there is a long line of works on searchable symmetric encryption, which addresses a special setting where the client is the owner of the data and wants to search over its encrypted data, say held in a cloud server. And in that setting, it's not a consideration to keep the data private from the client. More recent systems have incorporated SSE into extended applications such as CryptDB and Myler. And there have been other practical systems that support limited search functionality such as single keyword and conjunction queries. But recently there were two systems, BlindSeer and OSPIR OXD, that were concurrently developed, and they really achieved a breakthrough in combining provable privacy functionality and performance. Each system achieves different trade-offs between security, privacy, functionality, and performance, and are most appropriate for different application scenarios. But the weakness in BlindSeer, which is the focus of this work, was that the access control was not secure against a malicious client. Now, granted, the servers are also assumed to be semi-honest, but we see the fact that the client cannot be malicious as a more significant issue. In a database where this privacy of the client's query is not important, you can trivially implement robust access control by prohibiting queries that are not allowed. So in offering search privacy, BlindSeer shouldn't sacrifice on a basic tenet of database security. Now in BlindSeer there are two separate protocols. There is a search protocol to evaluate the query on the database, and a policy protocol to evaluate the policy on the query. In both of these procedures, the query is kept private using a cryptographic protocol known as secure function evaluation, which was talked about in previous talks in this session. But the vulnerability is that the client can submit entirely separate queries to the database search protocol and the policy check protocol. So our solution uses a simple trick. We still maintain the same architecture and we use secure function evaluation in both procedures, but we use a simple trick to prevent this vulnerability. Now in order to explain this trick, I'm going to again review briefly secure function evaluation. It was talked about in the talk on tiny garble, but I'll reintroduce the basic concepts. So in this primitive, two parties will engage in a computation that will allow one or both of the parties to learn the output of a function, while their inputs to the function remain secret. Our implementation uses garbled circuits, which is also mentioned in the tiny garble paper. In a garbled circuit protocol, we represent the circuit as a Boolean. We represent the function as a Boolean circuit, and a garbled circuit is essentially an encrypted version of that circuit. One party that we call the generator essentially replaces each gate of the circuit with ciphertext and chooses different decryption keys corresponding to the different possible inputs to that gate. This generator then transfers the garbled circuit along with the keys corresponding to its own inputs to the circuit. It sends these to the evaluator party, and the evaluator additionally obtains through an oblivious transfer the keys that correspond to each of its own inputs to the circuit. Once it obtains all these keys, it is able to decrypt the value out of the circuit. So garbled circuits are actually very fast for small circuits, and using the optimization called the free XOR technique introduced by Kolesnikov and Schneider in 2008, XOR gates in the circuit don't actually contribute noticeably to the overall computation time of a garbled circuit. Now, garbled circuit protocols are they preserve the privacy of the inputs, but they assume a semi-honest generator, meaning a generator that is trusted to indeed garble the specified function being evaluated. But on the other hand, the evaluator can actually be malicious. Alternatively, you can think of it as a semi-private function evaluation where one party can choose a function of its own choice, and the second party will only learn the topology of the function. We use garbled circuits in both the policy protocol and the search protocol in BlindSeer, but the client plays different roles in these two procedures. In the search protocol, the client acts as the generator of the garbled circuit. It generates a query circuit corresponding to its query, and that circuit is then evaluated on the server's end on the database. On the other hand, in the policy protocol, the query checker generates a garbled policy circuit representing the policy, and the client acts as the evaluator in this procedure, evaluating the policy circuit on its own query. It obtains through an oblivious transfer keys corresponding to its query inputs. So this is the root cause of the malicious client vulnerability, because nothing guarantees that the keys that the client obtains in the policy circuit evaluation at all represent the same query as the garbled query circuit that it produces for the search protocol. Now, in general, obtaining practical malicious security in secure function evaluation protocols is a difficult problem. Semi-honest secure SFE protocols are orders of magnitude more efficient, and although generic transformations of semi-honest to malicious protocols exist, they incur impractical overheads in general. In our case, we are dealing with a special case where we only need one party to be malicious, namely the client. And we already saw that garbled circuit protocols are secure against one malicious party, the evaluator. The problem is that the client does not play the role of evaluator in both the search protocol and the policy evaluation protocol. So our idea is to make the client the evaluator in both of these protocols. As the generator, the server will be able to cryptographically bind the client's inputs to these different circuits simply by synchronizing the keys that it will use to evaluate these circuits. You can think of this as giving the client one key for two different locks. The main question is, how can the server generate the query circuit without knowing the query? And the answer is to use a universal circuit that will take the query as input. Now, it's very nice that the Tiny Garble paper also talked about universal circuits. And it mentioned that you can generate universal circuit that will simulate any circuit of size k. Essentially, it takes the input description of a circuit of size k and some value and will output C of x. But the cost of those constructions are expensive. Perhaps using Tiny Garble will actually be relevant in this case as well. But in our case, we achieved efficiency a different way. So again, the known constructions of universal circuits just increase the circuit size by a tremendous amount. So inserting them into a garbled circuit protocol will be expensive and will certainly cause a performance hit in blind Seer. But in blind Seer, the query circuits, because we're using garbled circuit protocols, they do not hide the topology of the query. The query's topology is actually known to both the server and the client. So the topology is not private. And second, the private part of the circuit is actually monotone. All the gates in the private part of the circuit are either AND or OR gates for reasons that I don't have time to go into in this talk. But what we're able to do is come up with a very cheap construction of a universal circuit that will simulate any monotone circuit with a given topology, and it incurs absolutely no overhead in a garbled circuit evaluation. So I'll explain the construction. The construction is actually very simple. So think of the original circuit and replace each gate with just a question mark. And now define the circuit to take in 3 inputs to every gate. 2 of the inputs will be the original inputs, and then there will be a third bit that just determines the functionality of that gate, either an AND gate or an OR gate. Now, in transforming this into a binary circuit, we necessarily have to increase the circuit size by a factor of 4, but we're able to do that without increasing the number of non-XOR gates. So as you can see here, each gate is replaced with this gadget of 3 XOR gates and 1 OR gate. And because XOR gates, as I mentioned, come for free in garbled circuit evaluation protocols, the cost of evaluating this universal query circuit is no more than the cost of evaluating the original circuit. So in summary, the index server will garble a universal query circuit that it sends to the client. The query checker will garble a policy circuit. They will synchronize the keys that they use in both of these garbled circuits. And the client will then obtain one set of keys corresponding to its query that it will use to evaluate both of these circuits. We analyzed the performance of this improved system on the same database that the original system was evaluated on. It was a 100 million record database of mock US census data. And we showed, as expected, that the performance did not degrade. This compares the performance of the two systems for single-term queries, for three-term Boolean queries, and for more complex range queries. We also compared the performance of blind Seer to MySQL. Again, this time introducing parallelization inside the search protocol, which was not done in the original system. So this was sort of secondary work that we also did as a part of this project. And we showed that the system performs within a factor 3 of MySQL on all queries. And this difference becomes obviously less noticeable when you include the time it takes to transfer the payload of the database to the client. So in conclusion, our main result is that we achieved malicious client security in blind Seer, or robust access control. We improved our security cryptographically. There was no degradation in the privacy of the query, and no significant cost in performance. So thank you very much, and I'll take questions.
For the talk. So what are your assumptions about collusion between the query checker and the index server?
Right. So in theory, the query checker could be logically associated with the index server. We would actually, in our implementation, we assume that there is no collusion between the index server and the query checker. So we could not just simply logically associate them right here. But what we would have to change around, it would not be too difficult, and I can explain the details, but it would not be too difficult to run the query checker on the index server and then involve the server more in that computation. So you do need two non-colluding parties in that protocol, but we could logically associate the query checker with the index server or the server.
So I'm wondering about the case where, so someone has to decide the policy that the query checker is enforcing. And then if the query checker is malicious, it could try to learn more about the queries by adjusting that policy more than you would learn by the original policy.
Yes, but so can you clarify what your question is? So are you asking whether the query checker will learn anything about the query?
So if the query checker is malicious, it could change the policy in ways that would leak information about the query based on whether the query violates the new policy or not.
Yes, that is true. The query checker is assumed to be semi-honest, just as the index server is.
Okay.
Yeah, achieving malicious security against the server would be a great result for this system, but and perhaps you can see this as sort of a stepping stone towards malicious security against the server, but while we're able to achieve malicious security against the client, we're not able to achieve malicious security against the server.
Okay, yeah, so that makes sense then.
Yeah.
All of the other entities are non-colluding and semi-honest.
Exactly, yes.
Okay. Other questions? Okay, I want to thank
you very much.